Okay, so this is the general Frank Lab organization. If you recall, then basically all that we need to do is when you enter your data is specify, well, first enter your data in this, what you get from the scanner in these scanner folders, and then you create a bunch of config files that specify what type of, what is your actual data and what is the experimental design that you run your scanner on, and what type of preprocessing pipeline do you want to run. We just specify here in the preprocessing underscore something config file, and then what type of first level analysis you want to run, where you specify in this first level underscore something, the first level analysis label or ID or name. And then you just run a bunch of FL Basic scripts, which are the FL Basic import to import your data. And this basically imports your data from the scanner to convert it to analyze format and put it into this nice bits compatible structure. And then you run FL Basic preprocessing step, which you specify which subject and which preprocessing pipeline you want to run, and we'll run that individual preprocessing pipeline for that individual subject. And then you run first level analysis, just using, again, the FL Basic first level, and then you specify, in addition to the subject and the pipeline that you use to preprocess it, you also specify what type of first level analysis you want to run, and that is all. And for a surface-based analysis, the only conceptual difference is that you need to use, well, first you need to have run your data through FreeSurfer. So we need a way to specify to our pipeline that where is the FreeSurfer data, that we have actually run our data through FreeSurfer. And the second is that we will need to use a different preprocessing pipeline, right? So in our typical default preprocessing pipeline that we use for volume-based analysis called preprocessing underscore M&I space. One of the main purposes of this pipeline is to actually put the data in M&I space, in this reference space where you can do inter-subject correlation nicely, because every voxel, any particular voxel for any particular subject is located in the same place along the anatomy of the brain, or approximately the same place where we expect to have reasonably similar functionality. So that's where the M&I space volumetric, what M&I volumetric space is. For surface-based analysis, instead of running the analysis on the volume, we're going to be running analysis on the surface. And what that implies is that we are going to have FreeSurfer compute the actual cortical ribbon for that individual from the structural data for that individual subject. And then we are going to take the functional data, which is also a 3D volume that we get from the scanner, and we are going to look at the voxels only within the cortical ribbon. And that's what we are going to be calling the extraction of the functional data at the location of the gray matter voxels. And then once we do that, and once we extract the ball signal within gray matter voxels within the cortical ribbon, then we are going to run analysis only on those surfaces. So instead of having 3D volumes, we are going to have 2D volumes, because, well, 2D surfaces that over time that represent the ball signal, and we are going to be running first level analysis on those 2D surfaces instead of for every vertex on that 2D surface, instead of for every voxel on a 3D volume. But conceptually, the only thing that we need to do is actually get the proper processing pipeline to actually get our data in the proper space, functional, and that implies putting the functional and the structural data in the coregister to each other, and then we extract the functional data from the cortical ribbon, and then we are going to run first analysis just as we did for everything for volumetric analysis. So all of the FL Basic steps are actually, or most of them, they tend to be they will identify the type of data that you are using. If you are using volumetric data or surface-based data, they will run the appropriate things. So most of the processing of the entire things that you will do to run preprocessing, to run surface level or volume level analysis will be identical. It's only a matter of, and the scripts will adapt to having your data in surface and will run the proper analysis for you. And when you have the data on the volumes, it will run the proper analysis for you. So there are only a couple of things that you need to do differently when you want to do analysis on the surface space. And the first, so the two things are basically the ones that I mentioned. One is specifying where the FreeSurfer data is, and the second is changing the processing pipeline to actually put your data in the proper surface space. And the way to do that is we'll see how to do that right now, basically. The first thing is how do you specify that you have actually run your data through FreeSurfer? All that you need to do is remember that you have a file that specifies a config file. In this example, we call it example 01 config file. This is for every subject. You have a config file that specifies, it has a structural field and a functional field, where you specify the source of your data. Where is your functional data and where is your structural data? Well, if you want to run surface level analysis, all you have to do is make sure that in the structural field of your config subject level config file, you point to the same anatomical data that you use for running FreeSurfer analysis. Typically, that will be in a folder that is created by FreeSurfer and is called MRI, and the name of the file, the anatomical file, is, you can use either one that is called t1.mgc or mgh or .me, or one that is called brain mgc, mgh, or .me. Either one of those things are fine. So as long as you, in the structural field of this file that specify the source of your functional and structural data, as long as you point to the data that has been generated by FreeSurfer, the anatomical data that has been generated by FreeSurfer, and the pipeline, when you run the import step, will, in addition to just importing the structural data, it will also import the FreeSurfer generated files that it needs for running surface level analysis, and it will do that automatically.
Alfonso, can I jump in for a sec?
Yeah, please go.
So when you say you can use one or the other of those two volumes, have you looked into what's best to use, or and if not, are these, when these are used for co-registration, do they, does having something like the skull script or not matter?
Yeah, exactly. So the difference between the T1 and brain is whether you have the skull or not. So T1 typically has the skull, and brain doesn't have the skull. And in practice, I find that it typically works better when you do have the skull. So I like the T1 better, but I haven't seen that dramatic of a difference in either case, because the skull is typically not very visible in the functional data either way. So when you do co-registration, it doesn't matter too much whether you actually do have the skull or not. But I don't know. I typically use the T1 files myself, and I think that for other steps it makes a little bit more of a difference, particularly if you try to normalize that data. It's going to work better if you actually have the skull than if you don't. But the latest iterations of SPM is smart enough to work correctly with skull stripped anatomical data as well, so that shouldn't make too much of a difference.
And do you know if have you looked at just using the orig volume that's so that that is generated? So with FreeSurfer, there's an original volume that you provided, like a Nifty or whatever, and then it does, I don't know if it does any processing on that, maybe some resampling, and you get another file that it calls orig.mgz, and then it does some processing to try to make the volume, it does some tricks to the volume, like tries to normalize the white matter intensity and things like that as it gets processed along. So like the T1 volume would have that. Have you looked into whether or not that adversely affects the registration?
And which one is the file that should have all of those, the intensity normalization step? I didn't get the name.
I think the intensity normalization step, I think the T1 would already have that applied.
Right. You mean the orig? I see what you mean. You have an orig file, which is the original one, and then you have the T1, which has been applied a number of individual steps, like this intensity normalization and things like that, right?
Right.
Right. I don't know why I like better the T1, but I haven't done enough testing to actually be able to confidently say that one will be better than the other. So the only purpose that we're going to be using the structural data for in our surface level anatomical pipeline is going to be for co-registration with the functional. So I imagine that there won't be much difference which particular file you use, because the functional anatomical co-registration already use these kind of like information-based measures which adapt to having intensity profiles that are not quite linear or match between the functional and structural data. So I suspect that there won't be too many differences between using one or the other. I often just use the T1 because I visually like those better, and because they have the skull, which in older versions used to make a difference. In newer versions of SPN, it doesn't so much. So it's mostly for historical reasons. If you want to try with different versions and find that some work better than others, that would be fantastic information to have. But currently, T1 would be the default recommendation, lacking any additional.
Let me just flip this a bit and ask, so let's say you wanted to do surface-based analysis for the cortical, for cortical regions, and then volume-based analysis for subcortical regions. If you were to just point to, say, the same volume here, that could be the T1 volume, or maybe if we found that if you used something that was more closely tied to the original volume, like the orig.mgz or orig.nii that FreeSurfer generates, could you use that same one for both pipelines for the
Yes, definitely. Neither of the pipeline touches the original file that you feed into the pipeline, so that's perfectly fine. And you can actually use the T1 file as the origin for both an M&I space pipeline as well as for the surface-based pipeline. So that typically works fine. M&I space normalization already has all of these like intensity normalization things and all of the matching of the Gaussian intensity profiles for each tissue class and all of that integrated into the normalization step. So I, again, don't think it will make too much of a difference which particular version of the file the structural file you enter if you are planning to do normalization. But the short answer is yes, you can enter the T1 file from FreeSurfer as the source of anatomical data for either case, for you're running the surface-based analysis or the volume-based analysis, and that will work perfectly fine.
Okay.
And even for both pipelines. So if you are running a different pipeline for surface-based analysis and another one for volume-based analysis, you can still enter the same T1 anatomical data for both pipelines, and it will be perfectly fine.
Okay. The reason I asked that is so that you can cut down on having like two sets of subject info files.
Right. Two sets of subject info files for the two pipelines, you mean? Right, definitely, yes. You can enter just a single subject info file containing the actual T1 structural file and the standard functional data, and that will work for any pipeline that you use. You're exactly right.
Okay.
Okay, so this is basically how you specify that information and all that. Let me see if I have an example of these files in here. Processing pipeline sign example. So here, basically, where you specify the structural fields, you remember that in the config file for every subject, you just, instead of entering the data that would be...
Alfonso, can you zoom in on your file?
Right. Let me see if I recall how to do it. Do you see... Now, this only works for my main screen. So I can do
left side, there's a one. Look at that.
So can you see that?
Yep.
Yes.
Okay. So this basically where you specify the source of the structural data, you just point here to the T1 MGC file that is the output of FreeSurfer. We haven't yet come up with the best way, with a recommendation to do here. And Jason, I wanted basically your input on this. What do you think is best? It's best to keep FreeSurfer pipeline in a different folder that we're going to have basically for every subject, and then in here point to that. It's best to keep it inside this original subject files that we are entering here, or it will be best to copy them to the scanner? Another option would be to just copy that in this folder. So when you have the scanner folder, enter there also the results of FreeSurfer and have that as the raw data that you use for that particular subject. So I don't know which one of these to recommend and which one is going to be cleaner. In practical terms, all that the pipeline needs is for you to specify where your T1 file is. Doesn't matter where that actually file is located. So that gives us a little bit of flexibility as to what to recommend. Should we recommend people to copy them within these folders, or should we recommend them to have them in a different folder where they actually have been run? What do you think?
Well, so we know, barring some change, which actually I think Matthias suggested may be the case, but barring some change, in how free surfers data organization structure works. We need to have them. You need to have all of the subject directories of the free surfer processing output in a single
right
top directory.
Yep.
So I think we could. I'm fine with it being a pointer. If it's just one file for this purpose, we could copy the file too. So we're kind of doing that for when we do the derivatives in the pre-processing steps. We're copying over the I guess like the input file, right, that we're using for these, and then doing the pre-processing. So I'm happy either way there, but we do need to have something in here. So for example, so whatever that study is, study example, there would be another folder in here that would be the free surfer directories.
Right. There is one thing that is automatically copied by the pipeline. So when you import the data and the data, you are pointing to a free surfer generated structural file. In addition to this anat, func, and folders, it will also create one folder that is called surf, and will contain a copy of the minimal subset of files that it needs to be able to use the free surfer information, and that includes the I think it was. What was they called? The sphere.reg files, so lh.sphere.reg and rh.sphere.reg, and perhaps a couple of additional files, the pile, the white, the lh.white and rh.while and lh.pl and rh.pl files. I think those are the 6 files are the minimal files that are actually used by the extraction.
But when you say that it extracts them, it's expecting them to. So is that like during the import?
Right. When you run the FL basic import that basically creates all of this stuff, if the anatomical file that you specify in the config file is actually an anatomical file from free surfer, it will also create these additional directories with that information. That is where the import of the free surfer information happens.
Okay. So let's say you were to run some analysis and then you're like, oh, wait a minute, the free surfer, something got goofed up with the free surfer processing, or we went in and noticed that there was something we could correct, and then we regenerated some of this stuff.
Right. You need to re-import.
When we do import, will it update those files?
Yeah, import will overwrite basically all of that information with information that you are importing from.
That's the one tricky thing with having a copy is just making sure that copy is reflecting.
Right. Exactly.
Whatever file you want to look at.
Right, exactly. So, I mean, we could have a link within the scanner folder or something. I mean, in the scanner is where we put everything that is kind of like the raw data that we enter to our pipeline. So it would make sense to put a link here that points to the free surfer folder, perhaps for that subject. Or we could have a raw copy, but I think having a raw copy is perhaps, I don't know. I probably like better the having a link, but I think this is totally up to you. What do you think it makes most sense?
I mean, another option is that we have a free surfer directory that's only like it's links to the individual file. So within sub-example 01, there could be something that is the free surfer.
Right, we could have a different like free surfer folder that actually has a copy of the entire free surfer output or something like that.
I've tended to shy away from
having too many copies of the same thing.
Based organizations.
Yeah.
So I think let's just go with what we're going to do. So in my mind, what we will have though is in example, there will be a free surfer directory, right? Something. Does that sound reasonable?
You mean here in addition to the scanner directory, another file?
Like in the parent directory for the study. At that level. So.
And here you mean like example and have something that is called free surfer here that contains all of the free surfer stuff?
Yeah, like FS data or something like that.
Well, right.
The other option would be some repository of the free surfer data.
Right, because we are trying to keep this directory entirely bits compatible. So that's why we have the code, config, and then subfolders, and then derivatives for everything else. So that would break a little bit the bits kind of logic of how to store things. Having
what if it was in derivatives?
Right, we could have it in derivatives, have something like free surfer as a different pipeline, and that will make sense, I think, in terms of bits logic.
Okay, that's fine. The other option would be to go back to some like central repository, which I am not opposed to, but it seems like that is not, it ends up being not well adhered to.
Right.
Let's just have it this way, then let's do it this way. And then if we need a central repository, we'll do that down the road. Like if we need some central location where everything's run all at rerun or something like that, we'll do that.
Okay, makes sense. Okay, so whether you put it in derivatives and then free surfer and then one folder for every subject, or you just have a link, or have it in a central repository, the end thing that you need to specify is within the config file for every subject, you need to specify actually where that anatomical file is. And as long as it's an anatomical file, it's automatically detected. If it is the anatomical file that is generated by free surfer and it has the proper sort of directories and all of the things that the FL is looking for, then we'll import that information during the import step without you having to do anything else. Yes. And once you have that information, you will be able to run subject surface-specific steps during the preprocessing and during first-order analysis. So the next thing that you need to do if you want to run surface-based analysis is, in addition to actually pointing to that free surfer stuff, is actually running a surface-based pipeline. So that goes in here. When you have already imported the data, so you basically specify the information of where the structural file is and where the functional file is, and then you run a full basic import with your data. That imports all of the functional structural data. In addition, it will also import the free surfer information. And once you do that, all that you have to do is run a full basic and then preprocessing, the name of your subject, and then the pipeline that you want to run. We have an example pipeline created for M&I space that is going to be the default for most cases. I've also created a default pipeline that is called surface space, and is the default recommended pipeline for running surface-based analysis. And I'll show you what that does. The pipeline example that is going to be using if you don't create your own pipeline is in the folder in. Let me see what this is. Let's see if I can find it. M&I space, and here is surface space. Okay, so this is the M&I space pipeline. This is just a config file that specifies the individual steps, and that file is typically located in this folder, project in the software FL. You will have a preprocessing M&I space config file and a preprocessing surface space config file. The typical thing that you will do for your own analysis is, if you want to start with one of these pipelines or two of them, is just copy these pipelines to your own config directory. If you don't do that and you specify the preprocessing M&I space name for the pipeline, you will still use this version of the pipeline and it will actually copy it for you. But just for making it simple, I think it's best if you just copy your version of your config file, and that way you can just edit that version of your file in your own config directory and do whatever you want with it.
Can I make a suggestion, Alfonso?
Yes, please, go ahead.
The preprocessing _ surface space is not like a orthogonal to preprocessing _ M&I space. So would it be possible to change preprocessing M&I space so that it's like preprocessing volume M&I space, or preprocessing volume direct, or preprocessing volume indirect?
Oh, I see what you mean. So kind of like specify directly in the name that M&I is actually a volumetric pipeline, and as opposed to surface. That's what you mean,
right? So I mean, it turns out that if you're doing the surface-based analysis, then you're explicitly not going into M&I space.
Right.
But for volume-based analysis,
you could have something like subject space or something, right?
Right. You could be. You're always going in M&I space, but I think what's the bigger distinction for us is having one that is volume based, where you're using, say, indirect normalization along with a warp map, or you're using direct normalization because you don't have a warp map.
Right.
So if it was, I think of the things that we've talked about, those are the three different things. You may argue Well, yeah. So just that way, because M&I space could be either one of those two.
Right, I see what you mean. So how would you suggest we organize it? Having 3 preprocessing pipelines, one for M&I direct normalization, another for M&I indirect normalization, and another for surface, like free surfer type analysis?
Yes, that's what I would suggest. This is based on our conversation from last
Yeah,
week.
yeah, right. I recall this. I didn't get to do that change, but that makes a lot of sense.
You made an argument that said that I had asked you, well, why wouldn't you always do direct normalization? And you said, when you don't have a good field map, like so.
Yeah, exactly. So,
well, then you'd use direct. So I could see. It seems like we're going to want to do surface space analysis most times, but you're going to want to do one of those other two, and it sort of depends on what you have. So I would say if you have 3 of these these example config files,
right,
that would be helpful.
Okay. Okay. Let me know kind of like what names do you think it would make most sense, just to keep it relatively simple. So to differentiate between the 2 versions, should I use like M&I direct, indirect, or something like that? Or
I would say, yeah, pre-processing. You could do M&I direct, and then people just need to know that M&I means vol, or that not surface means vol. And M&I direct, M&I indirect. Is everybody okay with that, or would you rather have the word volume in there? You think that would be better?
I think it's fine. I think
M&I vol direct, M&I vol indirect.
In the documentation, it just needs that one line that says this is.
Sure.
Yeah. Because. Yeah.
Okay, so I would say that, Alfonso. How about M&I vol underscore indirect and M&I vol underscore direct?
Okay, keep in mind that the longer everything that the name of the preprocessing pipeline is something that you're going to write a lot, basically, because every FL basic command includes the subject ID and the preprocessing pipeline ID, and then some of them include the subject, so the first level analysis ID. So we want to keep them relatively short, just not to have to write very long names. But anyway, I'll leave this for later. Just send me an email saying what type of name or what names do you think it works best, and I'll change the documentation and the files to actually use that. Sound okay?
Sounds good.
Excellent. Okay, so and I'll also add in the documentation the 2 versions of the M&I space. So right now this is using the direct normalization, this example, and we will have 2 versions of M&I pipelines, volumetric pipelines, one for the direct and indirect normalization. But the only thing to point in here beyond what we've already seen when we're running when I explained these pipelines, is that we now have the ability to label individual steps. So basically, when you add one of these functional labels as original, that basically gives a name to the data that you had at this step of the pipeline. And this allows you to, when you run first level analysis, to point to different levels of your data at different preprocessing steps. So typically, when you run a preprocessing pipeline, the output of that pipeline is the last step of the functional data after you run the entire pipeline, right? And that's your functional data that you want to enter into your first level analysis. Adding labels allows us to have to run first level analysis on intermediate steps. So and that is perhaps useful if you have, we already have the functionality. If you have 2 levels of smoothing, for example, we can already incorporate that we want to use one level of smoothing or the other as the source for our first level analysis. But well, having labels gives us more flexibility. So you can basically add a label to whatever state of your functional data at any point within your preprocessing pipeline, and then you can refer to that particular functional version of the functional data when running first level analysis. This is for the M&I space pipeline. So this is for the surface space pipeline. So I'll go into detail about what this does now. So basically, you first start labeling the data. This is your original data. So if you want to ever refer to that, you just use the label original for that. And then we apply functional realign and unwarp on a field map. And this assumes that you already have field maps. If you don't have field maps, it will complain. So basically, if you don't have field maps and still want to run surface level analysis, just remove this portion from your preprocessing pipeline, and that will still run realign and unwarp. It won't use the field map information to try to correct for this inhomogeneities of the field map within the scalar.
Alfonso?
Yeah.
Is unwarp different than using the displacement map?
Yes, the unwarp refers to the in the SPM lingo is the is the motion by susceptibility interactions. And that basically means that when you are in a non-homogeneous field and you move within that field, then the shape of the apparent shape of your brain changes, because it looks like a funny mirror type of effect, right? When you are moving within a mirror that is curved, then the shape of your reflection kind of like looks differently. So the same thing happens within a non-homogeneous field map, that when you move within the scanner, if the subject is moving, then the apparent shape of the brain is going to look different, correlated with how the subject is moving. So the unwarp, what it does is try to correct for that, the relative changes in the shape of the brain that correlate with the motion of the subject. And the field map tries to correct for the static version of that. So basically the overall changes in the apparent shape of the brain corresponding to what the actual brain looks like outside of the scanner because of these inhomogeneities. So when you include this, for doing this like absolute difference between the actual shape of the brain outside of the scanner and the shape of the brain that looks within the scanner, even if there was no motion at all, that's why you need the field map information. And to correct for the motion interactions with the field map, you don't actually need the field map information. All that you need is to run the unwarp step, which will compute the actual first order derivative of the field map with respect of the motion parameters, which can be estimated from the functional data itself. So you can run unwarp without actually having field maps, and that will correct for the interaction between motion and susceptibility, but it won't correct for the static susceptibility distortions. And for that, you actually need the field maps. Does that make sense?
Yes. So we should always use unwarp.
Yes, generally the recommendation is to always use unwarp. If the effect of how important is to run unwarp depends a little bit on the strength of your scanner and the resolution of your data and many parameters. But so some people will say that if your data is relatively low, it has low resolution and it doesn't have very high field, then you might not need unwarp because it's not going to have too much of an effect. But I think I would recommend to use unwarp pretty much always. It takes considerably longer than just running realignment. So if you are in a rush, that's another reason to only run realign without the unwarp, because that will take 10 times easily as much time as just running realignment. But other than that, I don't see a good reason not to run unwarp by default.
Okay, great.
Okay, so this is what you will run if you actually have field map information, and just remove that from your particular pipeline if you don't have field map information, even though it's not totally recommended to actually run surface level analysis if you don't have any type of correct for those distortions. Okay, then we run ART to identify potential outlier scans. That's the same thing as with volumetric data. And then we run affine co-registration. And this is trying to co-register your functional data to your structural data. And the reason that we need to do that is because the free surfer step is run on the actual anatomical data, because it's the data that is high resolution, and that is going to allow us to estimate these surfaces in a very nice and way. But the functional data that we care about is in a different space, and is typically scanned a little bit later. So those two, the structural and functional data, might not be actually in the same space. So you need to co-register them for them to be in the same space. And that's why we need to do co-registration. And once you do that, then you have both your structural and functional data in the same space, and all the then we label that subject space data just as a label to that data in case you ever want to refer to that version of the data before doing the resampling. And now we do the resampling. This just takes your data. This assumes that you have free surfer information. If you try to run this without actually having run your data through free surfer and having entered that in the import step, it will complain. You will get an error saying that you don't have free surfer structural information. But assuming that you do have structural information and you have imported that as part of the import step, then you can just run this individual preprocessing step, and that will work just fine. And it will actually extract the functional data for every vertex of the free surfer FS average space surface. Now you're going to have two-dimensional data that is actually stored in files that are named in the same way as your original functional files, but instead of having a .ni extension, they will have a .surf.ni extension, and they will have a particular dimensionality because it just comes from the actual number of vertices that are in free surfer FS average space.
Wait, Alonso?
Go ahead.
So we might touch on this at some other point, but if we wanted to access, like if we just wanted to plot an individual brain's surface in their surface space, would we be able to? Because this, it sounds like it warps it to, or yeah, warps it to FS average space. Is there a copy of the functional data in subject space?
So you have this version of the data that's volumetric in subject space. So this is the three-dimensional data before the import step, and that is going to remain the same. That is going to be something like mydata.ni, right? And a nifty file that is a standard 3D volume functional, well, 4D functional volume. And then when you resample, you get something like mydata.surf.ni, and that is a four-dimensional also volume, but it actually contains time series of two-dimensional surfaces, and that is in FS average space already. If what you're
why is that surface in FS average space and not the individual subjects?
Right, so you are asking why don't we get the data in the actual surface of the subject before interpolating that into FS average? That's what you mean?
Yes.
So there is so when I say in FS average space, well, so your actual data is extracted at the individual subject location of every vertex, right? And let me see if I can specify that with an example. So let me see if I have an example surface data here. You have.
When you say FS average space, do you mean simply that it's
that it has been resampled to the proper dimensionality of the vertices? So you have so when you run FreeSurfer, you get a subject space surface that is just a file that is called lh.white, for example, and rh.white, that actually contains the white matter boundary for that individual subject, and that contains a variable number of vertices. That could be any arbitrary number. So for every subject, you have a different surface that contains different number of surfaces. And then you have the information in a file that is called lh.sphere.rec and rh.sphere.rec that tells you how to match that variable number of vertices within that subject surface to FS average interpolation. So FS average interpolation is basically a way to resample within the surface of that individual subject the vertices, so that you get your data in the standard in vertices that are all that when inflated look like a uniform tessellation in the sphere. So it's basically a resampling of your data within its own subject surface representation of the data. So I don't know if this is clarifying. So we could have imported the data. So the only difference is basically the number of vertices. We could export the data, import the data, the functional data into a surface file that will be in subject space that contains a variable number of surfaces for vertices for every subject. And then we will resample that surface level data into using the LH and RH sphere.rec information into the MNI tessellation. And the MNI tessellation is just this uniform tessellation in the sphere, because the sphere.rec files contain the information about how each of those vertices project into the sphere. You can actually interpolate within the vertices on that sphere to get the position of the vertices in FS average space within that sphere, and that is doing an interpolation within the surface level data. So it's not looking at the volume level data at all any longer. So you are first extrapolating the data from the cortical ribbon, and then once you have your surface level data that contains a variable number of vertices, because that's the each own subject surface, then you reinterpolate the data, but now it's a 2D interpolation instead of a 3D interpolation to actually get the data into FS average space. And that is just a two-dimensional interpolation of the position of those subject-specific vertices in well, it's a two-dimensional interpolation, but it's in the surface of a sphere, actually, where that interpolation takes place. I don't know if that clarifies. So this extraction does the two things simultaneously. It produces an output file that is a surface level file that contains a number of vertices that is the same across for every subject, and the number of vertices is the same as the first average surface number of vertices. And it does so by first extracting the data from the actual subject information from the location of the vertex for that individual subject, by doing a 3D interpolation, and then doing a 2D interpolation on the resulting surface on the resulting sphere of those surfaces, on the spherical representation of those surfaces, to actually get to the FS average space. So if your question is why don't we actually get two files, one that contains the actual surface level subject representation data for that subject and another one for the FS average space, I don't have a good answer. It's probably because it's not particularly useful to have that particular that version of the data, because they cannot be co-registered across the individual subjects, so it cannot be used for any further analysis. And it also doesn't help with the plots, because most plots assume that your data is already in FS average and use that for displaying, even if your data is actually, well, and even the plots that actually use the surface level information can do the interpolation back from the label. I don't know. Why would you want to have that? I could generate that intermediate step file if you want, but why would you want that? Basically, just.
Well, I would think it would. I mean.
Well, I think you were gonna.
Yeah, I was just gonna say, if you wanted to see where the functional activation results are compared to the gyri and sulci of an individual, not on an average surface spring. So if you wanted to see how that projected just specifically for an individual, if you were maybe just looking at the individual and wanted to create an image that was just showing how that activation occurred in an individual, and if you're not doing any further processing, like if you're looking at 4 different individuals, maybe, I don't know, comparing with ECOG stuff.
Sure. Well, I mean, any time you run this, you're going to want to look and see, okay, what does the individual speech minus baseline contrast look like in that subject's own space? And I believe that's trivial to go. So this idea of going to the FS average, like the spherical space, that's true. Like that's basically, you can just, when you load it up, you have these registration files that'll go, you can look at it in the subject space, just basically just a one-to-one mapping, right? I think is that correct, Alfonso?
Yes, exactly. There's a one-to-one mapping between the two of them.
Oh, okay. And then, so here's another question. This is a basic free surfer question, which I just sort of assumed wasn't a question, but maybe it is. Because we do this all the time, right? We say, okay, we have a one-to-one mapping from a vertex in the subject space to a vertex on the FS average surface, right? Mm-hmm. And we say, okay, that's how we do our labeling now. But so when in that subject space, has that surface already been interpolated so that there is a literal one-to-one mapping from one vertex to another, or are there more or less vertices, say, in the subject space, so that any given vertex might map to two vertices in the FS average surface?
Right. There is a different size of the number of vertices. So FS average has a default number of vertices that correspond to this tessellation of the sphere, basically, and that is uniform in the sphere, while the subject level surfaces contain variable number of vertices. So there is an interpolation needed to display that. But I think most of our, well, I'll have to check, but I think most of our display scripts should handle that interpolation automatically. So I can.
So that's sort of like, at least in terms of the labeling, that's been kind of going on behind the scenes.
Right, exactly. All of this is happening behind the scenes. Basically, that the surface level information is just like a nuisance to actually have different number of vertices per subject. It's just a product of how the free surfer actually computes those surfaces. But in practical sense, it would actually make perhaps even more sense to actually recompute. Actually, I think there is I'm not totally sure. I'll have to double check. I think there might actually be a version of the surfaces for every subject that is still in the surface in the subject space, but is in the proper number, in the FS average number of. So it's perhaps easier to interpolate the locations of the vertices on subject space that is to interpolate the actual whatever image you want to display on top of that.
So that's sort of my kind of follow-up to Saul's initial question. It has more to do with in what space we're actually doing the analysis. So the way this works, I believe, is that we end up shifting the data to a surface space, and then we apply, say, like smoothing to it so along the surface. And it seems like when we and then we do the first level analysis based on that outcome. So it seems like what happens here is that there's this actual this resampling prior to the smoothing and also prior to the first level analysis. And so I'm wondering, would it make more sense to do this interpolation as part of the second level analysis step? With the caveat that I don't think it'll make a whole lot of difference, and it may be that this is just it's fine. If your answer is because that's how FreeSurfer works, but that's the easier way to use FreeSurfer. That's fine too.
Right. I mean, it makes it a little bit more complicated to try to keep the different number of vertices per subject all the way up to the second level analysis. And it kind of defeats the logic of how we preprocess the data. So when we do preprocessing in volume space, we also do resampling to whatever space we want to have every subject in. And there's going to be our M&A space, and we typically choose like 2 millimeter isotropic voxels, no matter how you got your functional data. And in the surface level analysis kind of pipeline, it works in the same way. You typically want to resample your data up to whatever resolution and space you want to keep your data on, and from that point every subject is actually co-registerable between each other, and that makes life simpler. It's true that it's possible and it's feasible to do the other way, to keep the resampling all the way up to second level analysis, to do first level analysis all the way into the subject, but I think that it's unnecessarily complicated. Given the level of smoothing that we use for second level analysis, the additional smoothing that is incurred by actually doing some interpolation is totally minimal compared to the smoothing that we do to actually take into account the different anatomical structures across subjects and the level of smoothing that we typically use for both volume level analysis and surface level analysis. So I think it's perhaps just an unnecessary complication to try to do it that way.
Is there some argument for if we're doing like individual speech lab ROIs where if we translate everything into FS average space, then for each individual you need to make sure that you also have the individualized speech lab ROIs translated into FS average space?
No, FS average and subject space are exactly the same. They perhaps, I mean, you're missing some. So I'm not explaining clearly enough something. There's only a 2D interpolation difference. So imagine your subject-specific surface that looks at the actual ribbon or the difference between the white matter and the gray matter for that individual subject. That is like a convoluted representation of how the brain looks for that very specific individual subject. That is totally different from the surface of a different subject, and that is totally different from a third subject, and that is totally different from the actual FS average space. This is the surface level data. Then we take that surface that it looks like the subject brain, and then we inflate that. So we have vertices. Well, within that surface, we have individual vertices, right? And we have a lot of them. We have close to 200,000 vertices. So this is a very fine detailed interpolation of that individual surface or of that representation of that individual subject. So that is so the distance between two vertices is perhaps, I don't know, 0.2 millimeters. Is very, very close. Those are it's a very dense interpolation of the, well, representation of the surface in terms of individual vertices. So, and it's actually a triangular tessellation, right? So you have a surface and you represent the surface instead of individual nodes, and the nodes form triangles, and that you have a triangular tessellation that represents that surface, and it's a very dense one. And then you have that representation of the surface, and you inflate it into to a sphere. You continue inflating that until you have a sphere. And now you look at the tessellation of those triangles, how those look in the sphere, and you realize that they are not uniform, right? In the sphere, you would like to have a relatively uniform representation of triangles. So every triangle is relatively the same, so that when you smooth, you actually smooth in similar levels, amount of smoothing across the entire brain. So what you do, well, and you also would like to have the same number of vertices across the entire brain, so that you can compare one subject to another, because you want to talk about the surface of a subject and compare to a surface to a subject. Since you are representing the surfaces in terms of these individual nodes, you would like to have those nodes in the same location. So what you do, you have this very high dense representation, well, set of nodes that form triangles in the sphere, and you resample them into another different set of nodes that look as uniform as possible within the same sphere. And you can then take that tessellation that looks very uniform in the spherical representation of the data and put it back using the transformation that got you from the subject data to the sphere, just de-inflate it, so to speak, to get that tessellation back into subject space. And that will be what will be the difference between that subject space and the original subject space representation of the surface. It will just be a matter of the resampling of the same surfaces in terms of individual nodes. One of them will have like 220,000 vertices, and the other one will have 210,000 vertices. And they will be slightly in different locations, but they will all be within the exact same surface. They will be exactly in the same border between the gray matter and white matter of that individual subject. So the difference between the FS average space and the subject space in terms of is just a two-dimensional interpolation. There's nothing 3D about that, and it's only a matter of having two things constant, having the number of vertices constant, so that we can talk about one vertex in the sphere and being for one subject and being the same vertex for another subject on the same sphere, in the same location within the sphere. And the second is having the sampling of those vertices, the triangles that represent the entire surface on the volume, to be relatively equal size. So you want the triangles to be the equal size in one portion of the brain and another portion of the brain, and the way to do that is to have them resample into this relatively similar triangular tessellation of the sphere that FS average actually is. So I don't know if this helped a lot, but the reason why I was mentioning things is because there are not that much of a difference between the surface level data on the original number of vertices that free surfer gets and the surface level data on the FS average space. It's just a matter of looking at exactly the same surface, it's looking at the same triangular tessellation. It's just resampling it so that it looks the dots, those nodes in the spherical representation look exactly in the same place, and they have relatively similar sized triangles. I don't know if that clarifies or not.
So in that FS average space, would two different subjects have different placements of their gyri and sulci?
They are meant to be the same. That's what free surfer does. It tries to match the individual gyra and the sulci of every subject to the FS average representation of how the gyra and sulci should look if you look at the spherical representation of a standard brain. So FS average, free surfer has a representation of what these pretty pictures of the sulci and gyra, like images on a sphere. It tells you, it basically has a template that is actually on the sphere and represents how the gyra and sulci of individual subjects should match on a sphere. And what it does is basically it looks at the inflated brain of every subject on the sphere, and it tries to match whatever it finds in there in terms of where the gyra and the sulci are on the sphere to where they actually should be if the subject was in FS average space. And that's where the nonlinear transformation happens in surface level analysis. It happens all within free surfer. So as opposed to having like an MNIS pipeline where you do a nonlinear normalization of your data, of your brain, like a three-dimensional nonlinear warping of the data to make it match the template. In free surfer, this normalization happens on the 2D space. It first gets the surface of the subject, this very high resolution surface of the subject. It is inflates that all fully until it gets a spherical representation of that subject brain, and then it looks at where the sulci and gyra lie within that sphere and tries to find nonlinear deformation of that spherical representation so that the gyra and sulci are matched to the template, so that every subject should have on that spherical representation the gyra and the sulci roughly in the same location. That's the goal of a free surface normalization, intersubject correlation or normalization. Does that make sense?
Yeah, that does make sense. I think that, well, I may be wrong here, but Saul was thinking about when you do this thing, it's not trying, this resampling is not taking every subject and trying to morph it into the template.
Free surface already did that, right? So free surface already, it looked at the subject structural data, figure out how the sulci and gyra look for that individual subject, and it gave you a way to morph that into FS average space, a way to morph that into a brain that when represented on the sphere, it looks relatively similar to every other brain when inflated all the way to the sphere. It's still looking at the same surface at the subject level. It's actually telling you that when you inflate that subject level into a sphere, you will get a match between every location of every vertex within that brain. So it's trying to match the gyra and sulci location of the nodes within your tessellation of the subject-specific cortical surfaces, so that when those are inflated into a sphere, they look similar across subjects. Does that make sense? Does that answer the question?
Yeah, I think so. The one I was under the impression that the speech ROIs. So with the speech ROIs, like our labels, would they be different for each individual on the FS average brain?
Yes.
So,
well, think of it the other way: is that you take the speech ROIs on the FS average brain, and then you map them out to the individual. They're going to look different. The shape will look differently in that direction. Right. So what you're doing is so if you go in reverse, you're basically taking you look at the individual cortex, and you're basically mapping different shapes of things that should still represent, say, the precentral gyrus to the precentral gyrus on the FS average brain surface.
All right. Thanks.
Okay. So, any additional questions about this resampling? Is that clear enough?
No, I think that's totally clear now.
Okay. I should have pretty pictures to kind of explain this. It's all very kind of difficult to explain what is happening, all conceptually, but it's anyway, yeah. I mean, this free surface is a fantastic pipeline. It actually respects very much the anatomy of the subject, and it works fantastically. The only caveat is this whole correlation between functional and structural data, whether that is a good quality or not. But other than that, it's very when you are putting something, when you are thinking of FS average space, that is in a space that is actually very respectful of the individual anatomy. It's trying to find the location of individual gyra and sulci features in the individual's subject's brain. So it's a very nice, as opposed to MNI, which is volumetric normalization, that is just doing some sort of matching of 3D of the 3D features. This is trying to match individual two-dimensional features. So basically, the location of gyra and sulci. So it's doing a very, it respects the anatomy much more than what MNI volumetric normalization does, and the only thing that you get when you put your data in this average space is just a two-dimensional resampling. Once you have figured out what the actual cortical ribbon is, you want to resample so that the nodes that you are going to be using to represent the entire surface are relatively similar both across subjects and across each other in terms of the triangles that they look at. That's the whole normalization that is happening within FreeSurfer, and is happening in this subject space resampling automatically for you. So basically, when you resample your data, you get it already in FS average space, and that means that even though your data has been extracted from the actual location of the cortical region for that individual subject, it's still sampled into the same number of vertices across every subject, and in a way that if you represent it into a sphere, it looks relatively similarly equal space tessellation, which is actually, it's a nice math behind this. It's actually impossible to produce an exactly equal size triangular tessellation of a sphere, but you can. And the tessellation that FreeSurfer uses is a very good one, but there's still slight differences in the shape, in the sizes of the triangles, because it's mathematically impossible to actually compute a full representation of that surface in terms of the identical triangles. But anyway, they are very, very similar to each other in terms of their size. Okay, so we have the subject space data, and that is basically a .surf.me file that is also a 4D volume, but just has this different, has a very specific number of voxels because those represent the actual number of vertices across both hemispheres, and it has whatever number of time points you had your functional data on. And that's this step. Then we label that surface space in case you ever want to use that, and then we smooth different amounts in the same way that we did smoothing for the volume-based pipeline. So that you can look at the original data if you want, and it's with any level of smoothing, or you can use the fully smooth or partially smooth data, and then we label that as smoothing. And that's the entire pipeline. That's
Wait.
Sorry, go ahead.
Are those two doing different things? The two functional surface smooths? Why is that on there twice?
Yes, there are two. The same thing happened in the individual preprocessing pipeline for volumetric analysis. We have two smooth steps, and they are done sequentially. And the reason to do that is so that we end up with two levels, two different data sets, which have been smoothed for different amounts.
Sorry, I don't track well, so when you're saying that earlier, I didn't distinguish that they weren't the same word. My bad.
So basically, we take our M&I space data. This is the M&I space pipeline, right? We take our data, we put it into M&I space, then we smooth it for using a 4 millimeter full width half maximum kernel size, and then we smooth it again. Sorry, we smooth it again using now 6.9, and this strange number is basically defined so that the smoothing level of the second data set is 8 millimeters compared to the original data. So it's as if we had to obtain our original data and smooth it 8 millimeters instead of 4 millimeters. And that's done in two sequential steps instead of like two branching steps. Next. And the same thing happens in the surface level analysis. We get the raw data that has been resampled and it hasn't been smooth at all. Then we smooth it using this, and we smooth it using this other level. And this
so
number.
What is this? What is diffusion steps?
Right, and this is because we have our because smoothing on the surface works differently. Does smoothing on the volume, it works by convolving with a Gaussian kernel, and so you have a three-dimensional volume, and you just do a convolution with a Gaussian kernel to implement the smoothing. The smoothing on the surface is implemented as a diffusion, a series of diffusion steps. So diffusion is just you have a surface that is represented as nodes and edge between the nodes, and a diffusion just takes the value of a node and looks at it and makes it diffuse across the neighbors. So basically, every value of the node in the next iteration is going to be equal to the value that it was before, plus a weighted sum of the neighbors, of the values of the neighbors. So basically, this is like a heat diffusion equation, and what effectively does is kind of like a smooth data. It diffuses it. Smoothes the data, but on a particular surface. But instead of parameterizing it since it's not happening by any convolution of the Gaussian kernel convolution, it's actually happening by an iterative procedure of actually running diffusion, a number of steps. Then we characterize the size of the amount of smoothing by how many steps you are diffusing your data, and we are using these two levels of smoothing. At some point, I computed what this level of smoothing represented approximately in terms of a full, if we were to smooth the data using like a Gaussian convolution to give us a sense of how big these kernels were, the amount of smoothing. Do you recall what these numbers were, Jason? I don't recall what the numbers were. I think this is very small. This is roughly like a 4 millimeter smoothing type of thing. and this is relatively larger, like something like 7 or 8 millimeter smoothing overall. But I don't recall the exact numbers. I'll send you those numbers later on. Okay, but the point of this is basically to have, again, 2 versions of your data, well, or 3 versions of your functional data. One that hasn't been smooth at all, and then 2 versions that have been smooth to different levels.
And
So
the idea, I'm sorry, just this idea of doing 2 smoothing levels is sort of like a lab idiosyncrasy, right?
Right. Yeah.
Like you could just do one well-informed level.
Well, it's tricky, but I mean, different questions. The amount of smoothing affects the sensitivity. It doesn't affect anything else. So it affects the sensitivity or the power of your analysis. So there are different questions that can be, depending on the type of question that you're, for things like a speech minus baseline contrast, where you just want to look at the raw data, that you have typically a very high power and you don't need much smoothing. And for that, you typically want to use very low smoothing because you don't care about, you care more about the spatial specificity than you care about sensitivity, about the power of your analysis. But for other more subtle questions, when you're looking at for more typical scenarios, when you're looking at subtle effects or between different conditions or difference between groups, then you typically care about power a lot and you want to maximize power as much as possible, and that's why you do a smoothing. So typically, I would say that use the full level of smoothing. That's the optimal level for the typical questions, subtle questions we ask about, and only use unsmooth data or minimally smooth data when you really have power to, like too much power, and you really don't care about sensitivity that much, and you care more about the actual specificity of the things that you're looking at, and you don't want to smooth your data because of that. But I think the 8 millimeter smoothing for the volume data and this level of smoothing, the 40 effective steps of smoothing for the functional data, is reasonable, optimal level of smoothing for the typical questions that you want to ask your functional data. Only that when you want to look at things like speech minus baseline, and you know that you have more power than you need for those type of contrasts, and you don't care about individual difference between conditions and things like that, you might want to look at unsmooth data just to gain a better sense of the localization of those individual effects, spatial localization, rather than, because you don't need about that much sensitivity. But I think, I don't know. In general, the full level of smoothing is what I would recommend as the default. If I were to change this to only have one level of smoothing, I would strongly recommend to use the final version of it. So basically, the fully smooth data.
And when it's 30 here, does that mean the 30 nearest vertices, or does it mean?
No, it's applied 30 times. So that means each time that you apply smoothing, it does a weighted average of what the actual data was for that vertex and what the average of the values of all of the neighbors are. And so you apply that 30 times. And it means that effectively, if you were to compute the effective range, all the way up to 30 neighbors could potentially affect your data, but the actual level of how much they affect is an exponential decay. So the 30 neighbors, 30 steps neighbor is only affecting minimally compared to what is affecting the actual closest neighbor to your data, because they have like an exponential decay type of rate of influence. So I don't know, that's one way to see.
But does 30 apply to like steps, and then there are a certain number of neighbors that are affected, or is it 30 neighbors? I'm just trying to imagine like 10. If you start at one vertex, I could see how you could. So the nearest neighbors would be some set of 6 other vertices, right?
Yeah, there are always 3, and I think there are always 3 and sometimes 4. Well, no, there is variable as well. It's not fixed, the number of neighbors. It depends because of the way the tessellation is computed. But yeah, there is roughly like 6 neighbors. It looks like this hexagonal grid broken down into triangles, how the surface typically looks. So that means that you have typically 6 neighbors for every node, and for each individual step, you look at the average across all of those 6 neighbors, and you compute a weighted average of the value that you have for yourself and the value that you have across your 6 neighbors. And then you do that 40 times overall to do the entire level of smoothing. Does that make sense?
Just a related follow-up question. I thought when we discussed before in some lab meeting about the level of smoothing to use, that it was kind of recommended to use minimally smooth. at least in the context of my data. And I guess I'm just not completely clear as to why we would use one versus the other.
Sorry, I didn't fully understand. Could you repeat the question?
So previously when we were looking at the S-rate data, in some lab meeting I had presented some data, and I think it was Frank who recommended using like minimally smooth or using minimally smooth data, not the maximal smoothness. So I guess I'm just trying to understand why.
I don't recall exactly, but the typical scenario is, I think if what you were, I don't recall exactly the case, but if you were lacking power, I would typically recommend using the fully smooth data. If you were having some data that didn't quite reach the threshold, the parametric, non-parametric threshold, so the parametric threshold you use, I would probably say use the fully smooth data because that's going to give you higher sensitivity. If you are looking at things like a speech minus baseline and you are trying to figure out whether the location of the responses that you are looking at look in the reasonable places, and you don't care that much about the actual amount of noise in your data, you just care about getting a sense of the rough location of the activation, then I would probably say look at the minimally smooth data because that will give you the more spatial specificity. So kind of like the trade-off is between spatial specificity, the ability to tell where an activation actually is within the brain, and spatial sensitivity with the ability to find an effect, like a difference between two conditions in activation, if there is actually an effect present in the data. And that is typically a trade-off. You want to smooth data if you want to maximize sensitivity, and you want to unsmooth data or just the raw data if you want to maximize the spatial specificity.
Okay, that makes more sense.
Okay, that is all. That is the entire preprocessing pipeline for surface level analysis. Once you do that, you end up having this surface level data that you will still run through the series of steps in exactly the same way. So you will again run after import and preprocessing, and in this case you will use like a subject space of a different pipeline. Then when you go to first level analysis, you will just use exactly the same thing, only specifying here your pipeline, the pipeline that you want to import into your first level analysis, but nothing else changes in terms of how the syntax that you use or the logic that you have to use for the different processing steps, first level or second level analysis steps. These individual scripts will take into account that your data is in surface data instead of on the volume data, and it will adapt the type of plots that it will generate and the type of analysis that they are running. So, for example, when you run first level analysis on the surface, everything is pretty much the same. When you run second level analysis on the surface, it will give you only the ability to do non-parametric analysis because there is no way to the parametric version of this analysis of cluster level statistics is not available for surface level data. So that, but it will basically all happen behind the curtain for you automatically. So when you run the display or the second level analysis using the same syntax that you use for the volume level analysis, only now for surface level data, it will give you a display for surface level results, and that will allow you to do only non-parametric statistics instead of allowing you to do all sort of different things. There are a few, also the quality assurance plots adapt to the source of your data. So, and there are a couple of things that I'm still changing to make it as smart as possible. There is one quality assurance plots that I'm missing for surface level data that I want to incorporate yet, and it's still not there. But most of the times you will actually get your, let me show you an example of this. I think I'll just show data sets because I think that's the only one that we have so far that have been run through surface level preprocessing pipeline. So I'll just that as an example. So let me see. So let me add path for init. Let me recall, what was your experiment? You were in RAI, the one that is in subjects, sorry. It was this one, or it was some others, the one that had the subject space data?
No, it was this one. It was RHY01.
Which one? Sorry, I didn't get it.
RHY01.
RH101. Oh, okay. So the first one in here.
Yes.
One MRI and FO2. Yeah, okay, cool. Surface space. Okay, excellent. So when you run the, let's see if I have already QA plot. So when you run the QA plots, it will have created plots that are specific for that subject space pipeline, surface level pipeline, and it will have created something like, let me see. So instead of the results being projected on the volume, it will display the results projected on the surface. This is displaying the actual FS average surface. So these are actually shown on the FS average. What you were saying is that one thing that you were mentioning is whether it's possible to plot this on the actual surface of that individual subject instead of the FS average surface. That's what you were asking before.
Yes.
I'll add it. Currently, we don't have a simple syntax to do that. It's possible, but it requires a relatively complex syntax. So I'll add the ability to do that because it might be useful for these quality assurance plots to be generated on the actual subject space. Subject
I would say imperative. I would call it imperative to
okay,
be able to see this on the actual individual surfaces.
Right. I mean, those are two different things. That there are like three different sources of. I don't know. There's one additional plot that I want to create that I haven't created yet as part of the preprocessing pipeline. So we have all of these quality assurance plots are meant to kind of like help you catch different things, right? So you have this realignment plot that allows you to catch different problems during like in the realignment step. Then you have normalization that allows you to this is kind of meaningless for a surface level analysis because we don't run MNI normalization. So comparing the MNI subject, MNI surfaces MNI boundaries to your data is, you know that they are going to be in different spaces. That's perfectly fine. So we have this plot that allows you to catch. This is plotting the volume and the surface and the anatomical data for that individual subject. So if you look at the details of that is basically looking at, let me show you just for one individual slice. So this is showing let me just increase brightness. This is the actual functional data on the background, and then superimposed to that, you are looking at these yellow lines that are extracted from the structural data for that same subject. So these lines roughly represent the structural data in a way that is somehow transparent, so that you can actually look at the functional data behind it. And you see a good match between these yellow lines that represent the structural data, the boundaries in the actual structural data, and the image that you're looking at, which is the average functional data across all time points, then you know that you have a relatively good correlation between the functional and anatomical. So this allows you to catch potential problems in that. If there was a problem with the correlation between your functional and anatomical data, this type of plot would allow you to catch that. There is one plot that I want to generate that is still not generated that will allow you to catch some kind of stranger errors. So let's say that the structural data that you are using is perfectly correlated to the functional data, but these lines that you are seeing here, they are just obtained from the actual structural data. These are not the free surfer lines, the free surfer boundary lines. It would be nice to be able to display the same plot, but instead of these yellow lines being from the actual structural data, these yellow lines representing the actual surface that has been extracted by free surfer. And that plot, I will add it so that it is created because it will allow you to catch cases where the structural data and the free surfer generated surfaces have been, for any reason, put out of correlation. Those two things should always be in line. So free surfer T1 file and the free surfer surfaces should be perfectly correlated, but in some cases you might have, I don't know, the T1 file might have been modified and might have lost the correlation between that and the actual surfaces, and if that happens, we don't have an easy way to catch those issues. So for that, I will create those displays that allow you to catch those cases, basically, when the surface of one individual subject doesn't quite represent the surface, the anatomical data that it should represent. Then looking at the actual surfaces on 3D for that individual subject, it might be nice as well. I don't know which type of cases. I imagine that sometimes free surfer might produce like weird looking surfaces, right? If like these holes or cause this kind of like weird errors that might be simpler to catch if you actually look at the three-dimensional display of the three-dimensional surfaces for the individual subject, or what cases are you thinking that might be helped by having those type of displays?
Well, I think that so the display you're talking about is the subject's first level contrast on the subject's surface, right? That's what we're talking about.
Well, yes. I mean, the surface. I was mostly saying to represent in a three-dimensional view the actual surfaces of that subject, whether we superimpose the functional data on it or not. But
right. So
yeah.
I guess so. From a QA standpoint, I don't feel quite as strongly as from a interpretation standpoint. So you're looking, you want to see, I guess this falls under QA, but you want to see what the individual's speech minus baseline contrast looks like on that individual's surface anatomy. And not so much to determine if there are problems with the surface, but just to see, one, it gives you a chance to actually look at the subject's surface, and you can say like, okay, you can see if there's something that seems kind of wonky about how it's mapped, like a mapping from the surface to the FS average surface. I think it'll give you a better sense of that subject's anatomy, and it's it's the same as for the volume case. When we want to look at the individual subject data at the first level, we want to look at it not on the MNI volume, but in that subject's volume. In this case, it's the same thing. And FreeSurfer does a pretty good job, a better job of co-registering the anatomy, like normalizing the anatomy of this individual to the FS average surface, but it's certainly not perfect. And you can tell that it's not perfect when we look at the labels. Some brains, just the morphology is so different than the average template that it really messes it up. Like you can actually completely displace, say, like precentral gyrus. Rarely, but occasionally. So you'd want to see those. So it basically. So and Alfonso,
wouldn't be most. I mean, I'm trying to figure out which type of plots are most useful. Wouldn't be most useful to kind of like look at instead of having the functional data projected on the surface, look at the individual subject files, but having kind of like the curvature data or something like that projected on the surface. So
sure.
Or having the opposite. I mean, having the FS average space, but projecting the actual curvature subject specific curvature information onto that file to kind of get a sense of. I don't know. I'm trying to come up with which plots are actually most useful to detect which type of kind of like issues. If the problem is the potential miscorrelation between anatomical features for that individual subject, that might be more easily detectable if we are looking at the actual curvature information on like a FS average space or something like that. Wouldn't you think? Or than actually looking at the three-dimensional surface, which can hide a lot of the anatomy.
Surface. I see. No. I guess forget the three-dimensional part here. Let's just go back to two-dimensional surfaces. So like LH dot white, the individual subject's LH dot white.
Right.
The speech minus baseline contrast mapped to that with the and with the surface curvature applied to LH dot white. And I would say that LH dot white's not the best. I would like that LH dot semi-inflated or inflated surf that you generate would be. And the caveat that I'll just throw in here is that Alfonso, it'd be absolutely fantastic if all this stuff could just be in these QA plots and we just go through and we see everything. But FreeSurfer has tools that are
right
geared toward loading and viewing these surfaces. So, I don't think it'd be too much to ask for people and for me to show people how to look at these files using the FreeSurfer GUIs if need be. But so you could make an argument that says like, well, for the QA from a QA.
For the QA, what I mainly want is to facilitate or make it simple to detect common problems. So I mean, and you have more experience with FreeSurfer than anybody else. So you are the best person to kind of identify which ones are the most common issues that you might find in your data that might be worth and would be the best displays to actually easily identify issues in the data. So that feedback would be actually very useful for me to create, and I'll be happy to create the displays that are tailored to that. But I think the main goal is to try to come up with things that will make our life simpler in terms of easily identifying problems, so that when you look at those displays, you can tell confidently that, well, everything seems to be fine, and you can trust your surface level analysis because the correlation seems fine and the surfaces look fine, and I don't know, something that tells you that there haven't been any problems at a glance. So if you can think of any plots, and I'll be happy to optimize the plot generation to accommodate whatever you think works best.
Okay.
And I think what Alfonso was explaining before is projecting the outline of the FreeSurfer particle surface onto the functional volume, just to see whether those are aligned.
Right. I think this, like having these yellow lines being FreeSurfer generated surfaces, I think that might be useful to identify potential problems. And whether we want to actually have the surface, the anatomical or the functional data as the background, I'm not totally sure what might be most useful. Probably the functional, because that's ultimately where we are going to be extracting data from. And that would allow us to also identify problems in the correlation, but perhaps we are mixing two things. I mean, there could be problems in the correlation between the functional and the anatomical, and there could also be problems in how FreeSurfer computes the actual surfaces for those from the structural data. So it might be useful to plot the structural data with the FreeSurfer generated yellow lines, kind of like surfaces on one plot to identify the latter type of problems, and then do the former, like on the functional data, use those same FreeSurfer type of data, either that or this, to identify problems in the correlation rather than problems in FreeSurfer generated surface extraction.
I'd really like to see the FreeSurfer, sort of like the white matter in the peel surface. I mean, if it's
that can do both
on the
structural or on the functional. Would you prefer?
On the functional, and so it'd be nice to see it on the structural. But again, keep in mind that when we run these subjects through FreeSurfer, someone's going to look at every one of those and make sure that the FreeSurfer.
So on the structural data, they all already look nice. We already know that. Okay.
And so that'll be before you can run this ahead of time, but before like any final version of this is done, someone's will have gone through and just signed off that the FreeSurfer surfaces look reasonable, and determining whether there's some sort of very atypical anatomical abnormality in the subject, or if in the absence of that, still some really atypical thing happened with the reconstruction. So that that'll be done.
Okay, so I can easily. I mean, that was the kind of the plan, to have both the white and the PL surfaces on the functional data. That is kind of like the one plot that I was already aware that I was missing. But the question is whether we want to have something like this. So let me ask you. I mean, showing something that is similar to what we. Or just do it manually for 1 second. So the question is whether we want to have something. Let me remove something that is no longer necessary here. So just 1 second. I'm just gonna. This we don't need. Then, forget about the subcortical. I can remove it, but that's actually not necessarily. Let me actually remove it. Subcortical off. Okay, so these are the actual subject-specific surfaces, right? And I mean, right now I have it on the. I can change that.
Your surfaces, not the FreeSurfer surfaces?
No, these are the FreeSurfer surfaces, actually. These are the FreeSurfer stuff, but I don't have here the actual functional or structural data. I have like a reference. So imagine that I could generate something that shows you basically this. This is what I mentioned as the three-dimensional subject-specific surfaces. Is this useful? Is this useful at all? I don't know if would it be, no, not that, would you want to have anything projected on the surface of this data? I mean, looking at the three-dimensional look of those subject-specific surfaces generated by FreeSurfer, is that useful as a quality assurance plot or not, in addition to the other plots that we are talking about generating? That's what I'm not totally sure whether we actually need or not. Or projecting the activation on these surfaces instead of doing it on the FS average kind of like volume that I'm displaying right now. So
the latter, I think, would be very handy. And what I would suggest is instead of that surface, the peel surface, that you plot it on the
white matter instead of the peel surface.
That's like semi-inflated surface.
But the subject-specific ones or
right, the subject-specific one.
Okay.
Or do you have that?
No, we don't have subject-specific. Oh, okay. Yeah, we only create
white matter works. White matter would work, or even the inflated would probably work. So something
for the subject, we have the white PL and the sphere. And we could plot either functional data, curvature data, or I don't know. And we could add any type of like references slices if we think that is useful.
Why don't you and I talk offline about this?
Right. I can just think about
we're referring to the same things, because I think I could just show you in with FreeSurfer's tool.
Mm-hmm. What type of plots are generated?
One of the things I think would be an interesting thing to do here would be for us to try to actually do that. Would be to load up. I guess we don't have to use it. So with FreeSurfer's tool, you can load up the volume and the surfaces and the whatever other
individual slices
data, like surface or volume data that you want to load on there. I have not loaded up surface-based contrast map, but maybe I'll do that after this.
Okay.
But I think that, just going back to your original question, is that ultimately that's the check that you want to have. You want to be able to very easily take the individual, some contrast, say speech minus baseline or whatever it happens to be, and then look at them on each individual surface, right? And then maybe Alfonso can, in the meantime, convince us that looking at the FS average is exactly the same thing. I mean, I think it is, so long as there are not major. So the mapping is 1-to-1, but to be able to interpret the anatomy, I think is easier on the individual subjects.
Right. I think that in general it's easier to look at the FS average images because you can look at an inflated version of those and kind of not hide the activation, and that looks better than the subject level information. We either display this or the white matter or the sphere, and neither.
We do have that. So for each individual, you can look at the inflated surface. For each individual subject, you have an inflated surface.
Oh, right. I'm not actually saving that. You mean the LH inflated and RH inflated images? Right. I'm actually not saving those. So that's a good point. Perhaps I could actually save those, because I'm in the subset of minimal set of files that we actually need and we copy into the pipeline. I only copy so far the PL, the white, and the sphere.rec files. I don't copy the inflated. So that's why I say I don't have them, but I could copy them and have them imported as well, so that I could easily display them here. That's a good point. Yeah, because if we are going to be showing anything that looks like activation, it makes much more sense to look at inflated version of those. So yeah, I think it answers different questions. If you display them on the FS average space, on the FS average surfaces, it is kind of more directly related to how that individual subject is going to be, merge with other subjects. So when you look at a particular location within the brain, you know that particular location within the brain is going to be matched to whatever region you expect it to be on FS average space. Well, if you look at the inflated version of the individual subject surfaces, you never know whether the correlation has whether the between subject correlation for that subject has worked correctly for FreeSurfer. So it doesn't. It allows you to identify problems in the functional to structural correlation, but it doesn't allow you to identify problems in the free surfer normalization step. So if free surfer has messed up and co-registered your precentral gyros in a totally different location, you won't be able to identify that by looking at the surface inflated surface brain for that individual subject on top of the functional activation. But you might be able to identify that if you look at the FS average space inflated version of the brain, because that will be the activation will show in the wrong location. Or if instead of the activation you look at the cortical or the curvature, the pial, the gyral and sulcal features will look in the wrong location. So I don't know. Perhaps there is a point to generating both surface and FS average space type of displays for these things. I don't know. We can talk about that in more detail later.
Right.
I just wanted to kind of like show you what we have right now, what the different things what we could have potentially, and give you a little bit time to think about what you think might be most useful, and give me feedback on that, or we can meet later to kind of figure out the details.
And again, this kind of there's some bits of this are more QA focused, where other bits are more data interpretation.
Right. Exactly.
So
I mean, it would make sense for that subject surface thing to be in the first level QA.
Right. Yes, but although anytime we look at speech minus baseline, that is our first level, right, QA thing. So it just, I think it's Alfonso, we'll move on, and then we can plan to meet soon to just discuss, like, here's what I'd like to see, and you can, and I think I get what you're saying about the difference between, like, what you can pull out of these things, and a bit of it is, you know, we can go into more detail about like what would be like if we noticed that it looked okay in the subject space, but there was a bad mapping to the FS average space, like what that would mean, what sort of things would lead to that, and whether or not it's something that we need to actually include in the QA plots. Because a lot of this, if you just load up, you just run FreeSurfer's Freeview tool, you can look at all this stuff. So
right. I mean, I'm mostly thinking of it in terms of quality assurance. Like we are trying to build this kind of integrated quality assurance steps, so that when you run your pipeline, you can look at a bunch of plots and gain some confidence that everything ran correctly. So I'm still unsure or undecided as to which steps are going to be most informative in terms of evaluating the quality of the surface space pipeline. And for that, we can still figure that out. But yeah, I'm pretty much done in terms of what I wanted to display. The only thing that I was missing was to show this thing. Let me see if I have an example. In addition to this quality assurance plus, you can also look at something like that. And this is where you can look at individual contrasts. And again, this is the thing that you're going to say, yeah, this is all nice, but it would be better to actually show it in a different, in a surface that is individual for this particular subject. But this is, if you want to look at if you have run surface level pipeline and first level analysis, you can then run this command, the first level plot, to look at the individual plots that are generated by this pipeline at the surface level, and you can just change this so they use automatic scaling of this, and select the contrast that you want to look at, and that will display the contrast values on the surface. And this is looking at the actual FS average surface. You can change that and look at a different surface and look at the inflated version, but you don't have here, right, at least you don't have here the subject specific surfaces. You only have the FS average surfaces, whether inflated, the volume, or the sphere. But this is basically a simple way to look on the FS average space where the activation lies for that individual subject, and whether it lies in the location that you expect it to be. This is not part of the quality assurance plots. This is more for the evaluation of the results type of thing. So in this type of plots is where I think you were saying, Jason, that it will make more sense to have surfaces that are representative of each subject rather than FS average in here.
Yeah, for some reasons, or not reasons, but this is very nice. This is one subject.
Yeah, this is just one subject. So you specify here the first level plot, and then you specify the subject that you want to look at, the pipeline that you use for analysis, and that. If I do the same thing for something that has been, let me see if I have, for something that has been run with a different pipeline, so like the example, you will get different options, right? In addition to, like, you get a slice display type of options, or you can use something higher here. So this. Oh. So the same, exactly the same thing for a volume-based analysis will give you this type of displays. I should have changed this, but change that for a second. Probably it's probably minus 10 to 10 or something like that. Yeah. I don't know, this looks bad. Anyway, the point was to say that you use the same syntax to look at the actual contrast values for one particular contrast for one particular first level analysis. And if you have run if that analysis corresponds to volume level analysis, you will get all of these slice displays. And if you have that analysis corresponds to surface level data, then you will get the surface projection type of displays. And I will add or modify the options in these plots so that you can have additional options for the surface level, namely having the option to look at surface that are individual, specific for that subject rather than FS average, like what you have now. But the syntax is just that. Is after you run first level analysis, you can use first level dot plot and then the name of the subject, the name of the pipeline, and then the name of the first level analysis to display the different contrast. And this is the same kind of like interface that you use for the quality assurance plots. It's only that the quality assurance is always going to plot the first contrast that you specify and automatically create the plot for that for you. But if you want to look at a different contrast, you can always do that using this first level dot plot syntax. Okay, and that is all that I wanted to mention with surface level analysis. So as you see, some of this is still kind of like a work in progress. So let me know if you run into any issues or if you have any suggestions or if something doesn't quite work as expected, because we are still kind of like solving glitches and trying to improve things.
Okay, thank you so much, Alfonso.
No problem. And we exceeded the half an hour, so that frees me from talking about anything else.
Okay.
Okay, see you guys then.
Thank you.
No problem. Bye-bye.